All right, so let's look at this interesting paper from EPFL University. MIDI, Mixed Graph and 3D Denoising Diffusion for Molecule Generation. So this paper from EPFL. This work introduces MIDI, a novel diffusion model for jointly generating molecular graphs and their corresponding 3D arrangement of atoms. Unlike existing methods that rely on predefined rules to determine molecular bonds based on 3D conformation, MIDI offers an end-to-end differentiable approach that streamlines the molecule generation process. So we don't rely on the predefined rules. And our experimental results demonstrate the effectiveness of this approach. You see the samples from MIDI model that it generates simultaneously a 2D graph structure and a 3D conformation that is consistent with this structure. And because modern drug discovery requires the development of effective machine learning models that can correctly capture the vast chemical space and sample from it, these models need to understand properties of molecules that depend both on their molecule graphs and their conformation in the 3D space. So both topology and also the distances, the angles, everything. The conformation. We call it conformation in chemistry. The molecular graph determines the existence and type of the chemical bonds and allows the identification of functional groups in a compound. Unfortunately, existing generative models for molecules are restricted to one of these two modalities, while models that exclusively generate molecular graphs have been vastly researched. Current 3D molecule generation are, on the contrary, only trained to generate conformers, thus ignoring bond information. These models rely on a subsequent step that predicts 2D structure using either interatomic distances or chemical software such as OpenBabel. We propose now this, we call it mixed graph and 3D denoising diffusion. So previous diffusion models for molecules relied either on the Gaussian noise or discrete diffusion. MIDI uses both noise models simultaneously. The 3D coordinates are corrupted with Gaussian noise because there are continuous variables, the distance, the angles. And then while other components use discrete, for example, the atom type is discrete, it's carbon, oxygen, hydrogen, or the bond type is discrete, is either single or double or other types. So we add noise to atom types and formal charges at a faster rate than to the coordinates and bond types. Our second contribution is the denoising network. They use the transformer. They incorporate a novel ReGNN, which improves upon the popular EGNN layers. So these are the Gaussian and categorical distribution that enable efficient computation of the key quantities. So if you're not depending on your noise model and Gaussian diffusion, you can have either a Gaussian diffusion or discrete diffusion. You know, when it is discrete variables is discrete, your distribution is so categorical. So you see this matrix Q at time t. So everything is categorical. So the corruption process, if you're using Markovian, looks like this. The diffusion sequences are inverted by this marginalization over network prediction. It says that although this marginalization leads to more efficient training, it requires efficient computation of your denoiser and the integral, which is not always possible. So two main frameworks have been proposed. The Gaussian noise, which is suitable for continuous data, and the discrete space for categorical data. Gaussian diffusion are defined like this, and the posterior satisfies posterior of the transition conditions on X can also be computed in closed form. So the discrete diffusion considers that data point belongs to one of the classes. The transition matrices are square matrices of size d by d and represent probability because you jump from one type, one class to another at each instant of time. So Q at time t, what is the probability at each time that you jump from I to J or J to K? So Qij is this, Qjk is this. What is the, and all of them at the particular time that you say during your diffusion process. So given previous state Z, the noise model for the next state is just a categorical distribution over d possible classes, which reads like this. So zt minus 1 is a row vector encoding the class of z. Because a process is Markovian, the q bar is just multiplication of them. All of them are independent, so you can multiply. So you have a very nice closed form for forward. The posterior distribution, this posterior distribution, can also be computed in closed form using the Bayes rule and the Markovian property. So if this denotes a pointwise product, and whenever you see this is transpose of the matrix Q. So with this we can look at this and also they talk about SE3 equivariance with diffusion models. Because we have these coordinates R sub I, because node features are X sub I, edge features are Yij, so we can update R sub I, your coordinates of a graph, you can update it. And we denote one hot encoder of X and C and Y. And this is the resulting noise model. So we define Q like this. We have discussed this before. So we define the posterior as a product as well. And we calculate each term by marginalizing over the network. You know, to understand this mathematics, you only need to know the Bayes rule and marginalization. If you look at the proof of all of these things, it either uses Bayes or marginalization. These simple mathematical thing that you need to know as a background. So in our proposed method, we leverage an effective yet affordable EGNN layer for processing of the coordinates. However, we enhance these layers by exploiting the fact that when the data and the noise reside on the zero center of mass subspace, it is not necessary for neural network to be translation invariant. Rather than simply relying on a pairwise distance like this, we can therefore use other rotation invariant descriptors like cosine. So we therefore propose the following relaxed EGNN layer, and the REGNN layer combines a rotation invariant message function with a linear update. So this is a denoising neural network of MIDI jointly predicts the 2D graph and 3D graph. So the first one is extract 3D information. The second one, edge embedding. The third one, you calculate attention coefficients. Now that you have attention coefficient, you can have node embedding. Now that you have node embeddings, you can have REGNN update, and the graph embedding can be derived. So look at the inputs, R, X, Y, W. The outputs are the same variables, so you get the outputs. This is the denoising is the heart of diffusion. And if it is not expressive enough, you have problems. The error accumulates and you have problem of exposure bias because you don't have good unrolling trajectory. You have many problems. To improve the model's ability to process all features simultaneously, our new layer is integrated to a larger update block that processes each component using all other ones. Transformers have proved to be very efficient way to stabilize the self-attention, and we describe below the changes to feed-forward neural network and normalization because they are required if you want to have a E3 equivariance. So we define this pulse MLP like this. This is a projection of the coordinates on the linear space with center mass at 0. So this is how we project it. So the choice of normalization layer depends on problem symmetries. And also they talk about training objective. These cross entropies can be calculated. The distance of R, these coordinates should be minimized, the distance of predicted one. And so they did some experiments on QM9 data sets. So we need some measures, as I said, uniqueness, validity, most stable, novelty, connectedness of a graph. You cannot generate a graph like this that is not connected. So it should be connected. And the unconditional generation, also they used this data set, geom drugs, very important data set. Again, same measures, connected, novelty, uniqueness, validity. So we have different, also they compared MIDI with, for example, with EDM, different baselines.